I can start. Hi, everyone. Welcome to the C3 AI DTI seminar series for the fall semester. My name is Gauri Zoshi. I am an associate professor at Carnegie Mellon, and I'm co-organizing and co-hosting this semester's seminar series with Professor Richard Zhang, who is an assistant professor at the University of Illinois. C3 AI DTI features research that focuses on studying how artificial intelligence, machine learning, and big data can lead to scientific breakthroughs with large-scale societal benefits. So before we begin, we would like to pause and acknowledge the support from our academic and industry partners, for which we are deeply grateful. Our fall 2022 series was organized around two special themes, adversarial machine learning and distributed and federated learning. And our talks were scheduled to alternate between these two themes. So today we have our final speaker for the semester, Professor Sewoong from the University of Washington. We are really looking forward to his talk. During the semester, we had a variety of speakers from several universities and companies who are all listed here. And the recordings of all of these seminars can be found on the YouTube channel of the seminar series. So please check them out if you're interested. So today we are very happy to welcome Professor Sewoong to share his research with his talk titled Do Meta-Learning and Federated Learning Find Good Representations? Sewoong is an assistant professor at the School of Computer Science at the University of Washington since 2019. Previously, he was an assistant professor at UIUC. He received his PhD from Stanford under the supervision of Professor Andrea Montanari, and he was a postdoc at LIDS at MIT, working with Professor Devrat Shah. He has received many awards, including the ACM Sigmetrics Best Paper Award in 2015, the NSF Career Award, the ACM Sigmetrics Rising Star Award, and also Google Faculty Research Awards in 2017 and 2020. So without further ado, let's welcome Professor O. The talk will be 50 minutes long. And for the audience, please use the Q&A feature to submit your questions, and we will ask them on your behalf at the end of the talk or in the middle if there's a natural stopping point. So with that, let me stop sharing, and Sewoong, you can start sharing and begin the talk whenever you're ready.
All right, thank you so much, Gauri, and thank you, Srikant, for the kind invitation. Yeah, so meta-learning algorithms like model-agnostic meta-learning, also called MAML, and this type of algorithm has been quite successful in a wide range of applications, but the reason why they're successful has remained maybe mysterious or open, and this is our maybe first attempt in trying to understand and explain their success. And this is joint work with my amazing collaborators, Liane Collins and Aryan Mukhtari and Sanjay Shakutai at UT Austin. And towards the end of the talk, maybe in the last 5 minutes or so, I will make connections to federated learning, since this is a federated learning seminar series, and explain what our intuitions and findings imply for a very popular algorithm for federated learning called federated average. So this is the example that got me very excited about meta-learning back in like 2017 or 18. And it goes as follows. In the meta-learning setting, you have two stages, training stage and test stage. And then training stage, you get large number of tasks, and each task in this example is a regression task, comes with its own small number of samples, xi's and yi's. But each task has only small number of samples such that it cannot make accurate predictions on its own. But there is some structure or similarity across these tasks. In this example, they are all coming from sinusoids, but they're all different sinusoids. So the hope is that in meta-learning, maybe you can use meta-learning algorithms to train on meta-model, data style train, that throughout these tasks, that captures such structures and similarities of these tasks so that at test time, when you're given a new task with a small number of new data samples, maybe you can adapt to this new data samples and make accurate predictions. And this goes well beyond the simple two example, or supervised learning has been quite influential in many complex tasks. For example, here you're deploying drones at different environments, collecting data and completing tasks. So they're similar in the sense that they're using the same task, they're trying to solve the same task, but each environment is different. So there's a distribution shifts different between these different data collected. Nevertheless, you're hoping to use meta-learning algorithms so that you can adapt when you have a new environment where new drone is deployed. You can collect a few number of samples so then you can quickly, meaning small number of samples and maybe small number of computation, adapt to this new environment and complete the task. So what do we do in this meta-learning algorithm is that in the training phase, we have large number of tasks. Each one comes with small number of data. At test phase, we're given similar task, but with a small number of testing examples, so that we can use this samples to adapt to this new task so that we can have a good performance at deployment. So one maybe first simple attempt that we can think of is why not train a single model that is good for all the tasks by minimizing the average risk or loss across all the tasks and all the data samples across the tasks. So then at test time, we can take this single model and fine-tune it using maybe a few gradient updates using the data that we got for the new task so that we adapt to this new task. This we're going to call average risk minimization plus fine-tuning. And this essentially is pulling all the data together, because what we're doing is that we have n tasks, and we're looking for a model theta or theta star train that is minimizing the loss over all the data samples of all the tasks jointly all together. And at test time, we're going to take this and we get few samples from test task. We make a few gradient updates or fine-tune the model, hoping that this will adapt to the new task, have a good prediction for the new task. But this idea of pulling data together can be quite bad for meta-learning, because if you think about, because it has lost all the intricate fine-grained information about which samples come together from the same task. So if you look at the sinusoid example, for example, then you are given this samples from sinusoids, different sinusoids, and then you're putting them together, all of them, and feeding a single curve. And obviously, this wouldn't be good. And this has been observed many times. For example, this is an experiment from the breakthrough paper that introduced the MAML, where they took the ImageNet, and each task is constructed by collecting a subset of classes from ImageNet, let's say 3, and then next task will be another different 3 classes, and so on and so forth. And pre-training or average risk minimization plus fine-tuning, which is a natural baseline for them, is achieving about 28% on a 5-way classification task. So the random guess will be 20% in this case. And one shot here means that we are giving 1 data sample per class at test time. And 5 shot means that you give 5 data samples. So this is a few shot meta-learning scenario. And similarly, a little bit more complex task of 2D navigation, if you do pre-training plus fine-tuning or average risk minimization, then you get a performance drop that's significant. So you get a performance in the blue, which is average risk minimization, which is much worse than other kind of meta-learning tailored algorithms like MAML would achieve the green here. So what we want from meta-learning is that we don't want a theta that works well for all the tasks. We want a theta such that it provides a good initialization, so that after a few steps of fine-tuning in a specific task, whether it's in a training or task in the test, after fine-tuning, it has a good performance on the task that it was fine-tuned for. So there's only one difference in MAML and average risk minimization, which is that the objective that we're going to train a single model is going to be evaluated at, so it's going to minimize its loss on each of the tasks in the training, but it's not evaluated at the single point theta that we're minimizing. It's evaluated at theta adapted or fine-tuned by a one step of gradient descent on the tasks that we want it to work well on. And then we evaluate the loss on the same task, and we minimize the loss across the tasks. So now this one step adaptation is going to make all the differences. And at test time, we do what we do. We take this data, start train one single model, update using fine-tuning in the test task, and hoping it'll have an accurate prediction. So average risk minimization minimizes the average loss or risk through gradient descent update, which is this iterative procedure. And this is not adaptive in the sense that the gradients are all different tasks are evaluated at the same point at theta t. On the other hand, MAML is minimizing this adaptive loss using gradient descent on this loss. Now, the gradient update is going to involve Hessian. It's a D by D matrix because we have a gradient in the objective. But what we want to note is that now this gradient evaluation is adaptive in the sense that we're taking gradients of different tasks, evaluated at different points that is adaptive to each task. And when we implement it, we do it through two-loop algorithm, where in the inner loop, you do it in parallel. You adapt to each task by computing one step of gradient adaptation using only the local data. And using the adapted parameter in the outer loop, you evaluate the gradients across all the tasks and its losses and aggregate them in the outer loop. And the original motivation for MAML is that it learns a good initialization that can quickly adapt to new tasks, quickly meaning small number of gradient updates and small number of samples. But I call it original because there are increasing number of evidence telling us that maybe MAML is working so well in practice and complex tasks for some other reasons. And that's representation learning. Maybe it's learning a good representation that can be shared across all the tasks, even though it has never been specifically encoded in the algorithm of MAML. There's nothing telling it they should be learning a good representation. So what I mean by that is the following. In this training, we're learning a deep neural network in many of the cases. Then from the input layer all the way to the penultimate layer is going to be called the representation. This mapping from the input to a small dimensional nonlinear features is representation. And the last layer is going to be called the head. And what it means is that the conjecture in representation learning perspective of meta-learning is that in this some similarity sharing tasks in meta-learning, perhaps the similarity is that we have a single fixed nonlinear representation of the input that works well across all the tasks, and we only need to adapt the head for each of different tasks. And how do we test for such a conjecture? Well, this experiment from the MAML paper, this is for the paper from RRBV for 20, which first tested this conjecture, where they measured how much different layers of the representation is moving by looking at the similarity through CCA score before fine-tuning and after fine-tuning. So this measures how much the representation or the layers have changed. And you can see that the representation layers have not changed a lot. And all the change is happening at the head. Another way, so this is kind of confirming the conjecture, maybe that representations are shared across all the tasks. Another way of testing this conjecture might be that, well, you can design an algorithm, which they call almost no inner loop algorithm, ANIL, which explicitly encodes the conjecture that representations are supposed to be shared across the tasks. So in the MAML update of the inner loop, it freezes the representation layers. It only updates the head of the deep neural network. And the conjecture is that if they're solving the same thing, then MAML and ANIL should have similar trajectory in the training of losses for training and test loss, which indeed is true if you try it on the natural meta-learning tasks. So perhaps they're finding the similar solutions, although MAML has never been explicitly asked or designed to find a representation. And where we come in is we want formally to be able to prove this conjecture and show that MAML in some settings can find good representations. And what setting is it is a setting from what's called multitask learning or linear representation learning. And I'm going to use the term linear representation learning to refer to the setting where each task is a linear regression task. So the labels we have yi's are coming from a linear model, which is an inner product between the model parameter theta star for the task I, and then the input randomly drawn sample xi. Both are in d dimensions. So if you want to solve this linear regression task on its own, you need order d samples. The question people have asked is, how can we impose some structure in these models so that we capture the benefits of meta-learning, which is solving one task, helps you with solving other tasks. And the structure that people came up with to study meta-learning is the following. So theta star of I is the d-dimensional linear parameter. And when you put them together, they should span a k-dimensional subspace where k is a much lower dimension than the ambient dimension d. So all the thetas are lying in a low dimensional subspace. If so, then we can come up with a ground truth representation, let's say B star, which is a D by K matrix. So that it captures all the subspace, the column space of B star captures the subspace spanned by theta stars, so that all the parameters theta star can be represented as the representation B star, which is a D by K tone matrix, and there's no I because it's shared across the tasks. And then a task-specific head, which is a k-dimensional vector that represents the specific task's parameters, which is W star of I. And why does this capture the benefits of meta-learning? Is that if this is the model, then you can use all the other tasks in your training to learn the good representation B star. And once you have it in a new arriving task, you can solve it with only order k samples because you only really need to estimate the head, which is a k-dimensional vector. And I'm calling this representation and this head because if you're familiar with linear neural networks, in this case, the two-layer linear neural networks, the input layer is dimension d, and the hidden layer is dimension k with no activation. And that first layer is what we call representation, represented by d by k matrix B star. And then the head will be just k-dimensional vector, which will be a W that we call a head. And before, and there are many algorithms that can solve this problem, and people have studied this in both theoretically and algorithmically. And that's not our interest. We're not interested in designing a new algorithm that solves this linear representation learning. Instead, what we are interested in is answering the following question. If you follow the natural gradient descent for either average risk minimization or MAML, then do these algorithms or either of them learn the true representation they're going to recover under this setting? But before we get there, let's see what people have done to study this setting. And it was mostly studied under the lens of matrix completion and matrix sensing, and very recently also. And this kind of connection is clear if you realize that the samples that we get from the ith task, let's say yi, can be represented as inner product between two matrices. The first one is a known measurement matrix, which is almost zero everywhere, except for one column where the matrix entry for the column is the input data xi. And the other matrix is a low-rank matrix where the tall part is the representation B star, which is D by K matrix. And then the wide factor is the concatenation of the heads for n different tasks. So it's a K by D matrix, K by N matrix. So now we have a low rank unknown parameter that we want to recover that we measure through linear measurements. This is a special case of matrix sensing, and this problem has been studied recently, where we can use either alternating minimization, obtaining gradient descent, or nuclear minimization to solve this problem. But the analysis gets a little bit more intricate because usual assumptions do not directly apply. For example, if you're going to use matrix sensing techniques, then we need the measurement matrix to satisfy RIP, which roughly translates into it being a dense matrix with diverse entries. If you have that, then you don't need any conditions on the low-rank part. But if you have a structured measurement matrix, like in the matrix completion case, where your measurement is just a single entry, then you need to counter this with diversity in the row rank part, which is encoded through incoherence properties. In our case, we're something in between. We have structured measurement matrix, sparse in its columns, but one column we have is diverse and dense. So we only need to counter this with diversity in the task matrix W star. What we need is all the heads, k-dimensional heads W star i's to be diverse, which is captured by W star having a smaller condition number, which we're going to call task diversity. Again, there has been a lot of work designing algorithms specific to solving this problem. Those algorithms tend to have multiple heads, meaning they keep track of these low-rank parts in the algorithm and try to estimate all the heads for different tasks. The question we're asking is different. We don't want to design new algorithms. What we care about is that if you have a single parameter algorithm like average risk minimization or MAML, and apply that to this specific data, then do they learn the ground truth representation they want to recover? Was there a question, Gary, or not? If anyone has a question, this might be a good time to take a pause.
No questions yet
Sure.
in the chat.
Sounds good. All right. So what does MAML do in this representation learning setting? So MAML, or is sometimes called a gradient-based algorithm, as opposed to representation-based meta-learning algorithm, because MAML doesn't encode anything about learning a representation. It's only defined through the gradient updates that it performs, which in the linear representation learning setting translates into the following, which is in the inner loop, you'll be adapting to its task. So you start from the central parameters head WT and representation BT, and then you run a one gradient update step locally on the local data for that task, update this adapted head and adapted representation. And then out of loop, you evaluate the gradients at this adaptive representation and heads. And also there's a Hessian involved, and you update your central parameter WT and BT. One thing to note is that there are many different versions of MAML that people have proposed. You can do multiple gradient updates. You can add L2 regularization to kind of keep it away from drifting too far, or you can drop this Hessian term for computational efficiency and just run the iterative updates. In this talk, we're going to focus on just two variations. One is what's shown on this slide, which is one gradient update MAML, and the other is first order MAML, which is just dropping this Hessian from the update. And ANIL is another variation where we are explicitly encoding the fact that we want to find a good representation. So there's only one difference, which is that in the inner loop update, when we adapt these parameters, we're going to freeze the representation because we know it doesn't need to adapt, and only adapt the head. just the last layer of neural network. If this was a deep neural network, and then aggregate the gradients as we do and perform the outer loop. So because ANIL is explicitly kind of encoded to learn good representation, in the setting of synthetic experiment with linear representation learning, perhaps it's not too surprising that ANIL is, and first order variation of ANIL is learning good representation. And because average risk minimization pulls all the data together, in this case from all different linear regressions, maybe it's again not surprising that it's not learning the representation. But it's perhaps surprising that this MAML, which is never explicitly designed to learn any representation, when applied to the specific data, learns the ground truth representation as well as the ANIL algorithm.
Sewoong, can I ask a quick question since you're so in the when you described the MAML algorithms, there was a Hessian. You said that there are variations of it that does not compute the Hessian. Is that what you said? Or
right. So I'm going to look at two algorithms. One is MAML, which is exactly this one, which includes computing the Hessian and multiplying the gradient by it. First order MAML, FOMAML, is going to be the one that's updating almost identically, but just drops this Hessian, just set it to 0, and just updates the gradients.
but if you drop it, then the intuition you gave earlier, I don't quite understand, because I thought you said you're trying to minimize Fi of X minus gradient, right?
Right. So that one doesn't minimize the same loss.
Okay.
It's not clear what that one minimizes.
Okay.
But we are approximating it, hoping that it works well for meta learning, and we prove that it actually does.
Okay.
In this kind of theoretical setting.
Okay.
And in practice, it works well too.
Okay. Even though the intuition, the original intuition is somehow not captured when you don't take the Hessian.
Right. Many variations of MAML, it's not clear what loss it's minimizing. Oftentimes it's defined by bi-level optimization or just through the iterations like this. So you cannot just write down a loss such that the final thing you get is a minimizer of. That I don't think happens that often.
Okay. Okay, thanks.
Thanks, Riku. All right. So with this is a statement of our informal main result that we can show, which is that under the standard assumptions of MAML and ANIL, and the first order analogs of MAML and ANIL, they recover the ground truth representation that we want exponentially fast in this setting of linear representation learning, where data comes from this setting. And we can also show that the sample complexity analysis for finite sample case ensure that for each task, we need number of samples proportional to d over n plus 1 times k cubic. Ideally, then everything works and we recover the ground truth representation. Ideally, we want this to be order k so that the number of samples that we need across all the tasks, which is k times n, will match the number of degrees of freedom in the problem, which is roughly k times n or k times d. But it's not clear if this can be improved. Other algorithms which are tailored to solve this linear representation learning also require the k squared or k cubic dependence. And it's an open question as of now, whether it is also necessary or not. But the intuition why these algorithms work, as I will kind of be more detailed later, is that the inner loop has adaptation of the heads W's that allows us to harness the diversity of different tasks so that we can improve our representation in all directions of the key directions that we care about. On the negative side, one can show that this is a follow-up by my collaborators where they've shown an information theoretic lower bound saying that there exists constructions where average risk minimization will probably fail. and to compare or track our representation that we have throughout the iterations of the training and the ground truth representation, we need something that can handle the ambiguity that the solution is not unique, because those of you who are familiar with matrix factorization will quickly realize that you can multiply the representation B by any K by K invert of matrix A on the right, and multiply the head on the left by the inverse of the matrix A inverse, and you get the same linear neural network if you're visualizing it as a neural network, or same low-rank matrix if you're visualizing it as a low-rank matrix problem. So we need a measure that captures this ambiguity, and we're going to use principal angle distances between two subspaces, which is roughly the largest angle you can make with two lines in these two subspaces. So let's look closely at the dynamics of the gradient update for average risk minimization to see why it fails to recover the ground truth representation. So if you look at one step update at the outer loop of this single loop of average risk minimization, the representation in the next step, BT plus 1, is going to be a combination of mixture of two parts. The first part is the prior representation BT, it's a D by K matrix that we want to forget, which is multiplied by a K by K matrix that we're going to call prior weight. The next term is the ground truth B star that we want to learn, again multiplied on the right by another K by K matrix that we're going to call signal weight. So ideally, you want this prior weight to be small in all K directions so that we're forgetting the initialization, which doesn't help us in any way. And we want the signal weight to be large in all K directions so that we are learning this B star in all directions. But there are two issues with this dynamics of average risk minimization. The first thing is that if you look at the prior weight, then it's only reducing in WT transpose, it's just rank 1 matrix. So it's only reducing the BT in only one direction. So it's going to take a while to forget the initialization. But more crucially, if you look at the signal weight, then this is also a rank 1 matrix, but not only is it a rank 1 matrix, if you look at the column space of this K by K matrix, which is the average of the model heads, then this doesn't change over time. So this is the important vector because this is the one that's applied to B star. So essentially, we're only seeing B star throughout this gradient descent through only one slice or one direction among all K directions of B star. So this obviously is not going to learn the ground truth representation, which can be made precise in this work by my collaborators, where they showed that for any number of iterations, any step sizes, and any distribution of heads, you can show that for initialization B naught, there exists a ground truth representation B star, such that no matter how close you start this gradient descent, we will not make any progress beyond, let's say, 0.7 times the initial distance. So it's going to fail learning the ground truth representation. But on the other hand, if you apply like adaptive algorithms like ANIL, MAML, and their first order variations, then they can recover this ground truth representation. And the gradient descent dynamic, again, can be decomposed into two separate components. First one is the prior representation multiplied by a different K by K matrix. We're going to call prior weight again. And next one is the ground truth times another K by K matrix. We're going to call signal weight. So ideally, what we want is this average of WTI transpose, and then the average of W star I and WTI transpose, both of them to have well-conditioned condition number so that we can reduce BT in every direction and we can retain B star in every direction. So what we know from our assumption hand task diversity is that if we replace those by W stars, the ground truth heads, then we know those are good. Those have small condition number because that's part of our assumption. So what we need is this WTI, which is the one-step adapted version of the head in the inner loop of this algorithm, to be adapting fast to each task so that it's closer to this new task ground truth head W star I, and it's far from wherever WT it studied this one-step gradient step from. If we have that, we can show that the prior weight is small, so we'll be forgetting the initialization fast, and we have signal weight that's large in all directions, so we can learn B star. So task diversity, which is our assumption, and head adaptivity or fast adaptation of the head, which we haven't proven yet, is the key to achieving good performance. So challenges in proving this representation learning is the following. So now we need to show that this head adapts fast to these new tasks. So let's look at the dynamics of the update in the inner loop for the head. So you start with from the WT and apply one step of gradient descent locally. Then after the update, it can be decomposed into two parts. One is the prior weight, or K by K matrix, times WT that we want to forget. And another K by K matrix, we're going to call signal weight, times the W star, the ground truth task head for that task that we want to recover or adapt to. And to show fast adaptation, we need the prior weight to have small spectral norm, and we need W's in the outer loop to have bounded norm, and we need the small singular value of the signal weight to be large enough. But showing this is complicated. It would have been easier if we're allowed to change the algorithm by either orthonormalizing BTs or adding regularizations. The analysis could have been made easier, which we don't want to, because the goal we have in this project is not to design an algorithm that works well in this setting, but instead to analyze the natural gradient dynamics of ANIL, MAML, and their first-order variations. For that, requires an intricate six-way induction that I'll show you later. But with this, we can show that if we, for now, to state the first result, if we assume that we have infinite samples at each of the tasks, and we assume the task diversity is diverse, or the condition number is small, then we can show that with a small number of step sizes, alpha and beta, inner loop and outer loop, all of those algorithms learn representation with distance decreasing geometrically. And the convergence rate is determined by the step sizes and how diverse your tasks are. But remember that ANIL and first-order ANIL are more tailored for representational learning. And where it shows up is that they require much more relaxed condition on the initial distance to the optimum. You only need order 1 distance for it to work. On the other hand, MAML is not tailored for representation learning. So the cost it pays in this analysis is that the distance required for the initialization is more strict. It needs to be small, like the condition number to the -3/4. And the first order MAML drops this Hessian from this dynamics. So it needs more strict assumption. The distance needs to be condition number to the -1. And you need an extra condition that all these heads, when you put together and average them, needs to concentrate around 0. And we also have finite sample results in the paper, but these analyses are not just the artifact of our maybe weakness of the analysis. This is in fact true if you run these algorithms, compare them on a synthetic data generated from exactly the linear representation learning setting that we are analyzing them on. So with the random initialization that might not be particularly good, ANIL algorithms learn the representation. MAML and the first order MAML doesn't, because the initialization is bad. And even if you give good initialization, if you design this task heads such that the W's averaged over don't concentrate around 0, then first order MAML is going to drift away, and MAML will still learn the ground truth representation, but at a slower rate. So this is the analysis we need to do for showing our result. This is a complicated analysis that involves 6 different hypotheses to hold throughout all the training timeline, which imply one another in a complicated way. But let me try to give you just a maybe high-level idea of what they mean and what they are encoding. So there are 2 important dynamics that we need to control. One is the representation update at the outer loop. We need to forget the initialization and learn the ground truth. And the other is at the inner loop head adaptation to each task. We need to make sure that they adapt to learn the diverse ground truth heads and forget the initialization of the fine-tuning that they started out with. And for that, we need to show at every time step the WT, the head representation at the head of the model at the outer loop doesn't diverge, it's bounded. And we need to show that this prior weight for the head update is small at every time step. And we need to show that the prior weight for the representation update is small by showing that this psi part is well conditioned. And using this, we need to show we make progress every time step because now prior weight is small and we have geometrically decreasing distance to the optimum. And I don't think I will go into the details of how we prove it, but I'll probably just mention that this is not a simple induction where every time step all 6 are satisfied, and that implies that all 6 in the next time step. You need to do it in an intricate way, showing first 3 conditions are met, and that implies at time t+1, the next condition will be met, which implies the next one and the next one. And right, so we have analyzed this MAML algorithm, which was designed for a completely different, maybe intuition for meta-learning, which is that we're looking for a good initialization that can quickly adapt to different tasks. But under the lens of linear representation learning setting, we were able to show that both ANIL and MAML algorithms are effective representation learners that can find the ground truth representation quickly. And maybe, perhaps that's why MAML is working so well in the more complex tasks that involve nonlinear representations and complex deep neural networks. And now I'm going to change gears a little bit, since this is a federated learning seminar series, and try to explain what it means, everything we learned about analyzing MAML and how it's learning good representation, what it implies for federated learning. And this is mostly based on a follow-up work by my collaborators, which I'm not involved in. So mostly I'll be presenting this work and making connections. So let's get started. So in federated learning, we have a server that wants to learn, train a model, and the data stays at the client. You never share the data for privacy reasons, but you nevertheless want to learn a good model, so you're allowed to share the models and model updates. So one algorithm, which we call distributed stochastic gradient descent, how it might do it is that you send the current model from the server to the client, and the client computes the gradient evaluated on their local data, and updates the model with one gradient step and sends the model difference. And now server aggregating all these model differences, updates its global model and coordinates this or federates this training. So this is exactly the same as average risk minimization that we saw in the meta-learning context. It's just implemented in a federated way. And people notice that here in federated learning, the cost of communication is kind of bottleneck. So they designed an algorithm called federated averaging, which is one of the most popular algorithms in federated learning, which performs, let's say, multiple tau steps of local gradient updates before communicating with the server. And notice its similarity with MAML. So what it's doing is that the server sends the model, and the client, on receiving this model, updates the model, fine-tunes it by k, let's say, gradient descent step, or tau gradient descent steps. And after that, sends the model difference between the initialization, where it started fine-tuning, from the end of the fine-tuning. The difference is sent as a delta. It's aggregated, updated server, and continued. So original motivation for federated averaging is communication efficiency. But there are increasing number of results showing that perhaps it's learning good representation also, like MAML was doing. Although this evidences came much earlier than our analysis. So for example, this is the similar task that we use for understanding MAML, where you take like C400 in this case, and each client is constructed by taking a subset of classes from C510, and you train two models, one with federated average and the other with distributed SGD, and see how they perform when you're given a new client with new classes of examples from a class that has never been seen before in the training. So it's a generalization and also meta-learning. And in this personalized federated learning accuracy, you can see that changing the number of classes, which changes the heterogeneity across classes, across clients, doesn't change things much. But what it does change a lot is whether you train with federated average or not. So federated average seems to work much well across different tasks, suggesting that maybe it's learning a good representation. And you can do it more explicitly to try to test this idea and measure how much these different layers in the representation are changing in fine-tuning of a model that's learned through either federated average or distributed SGD. And we can see that the federated average representation layers change much less compared to a model that's trained with distributed SGD when they're fine-tuned, meaning that maybe there is a good representation and it's good across all the tasks. And similar thing has been observed for more natural data set. This is EMIS, the data set of handwritten digits and characters, where the data is partitioned into users who have written these data sets. So it's a much more natural partitioning of federated data set. And you can see on the left, if you use federated averaging type of algorithms, you get the best one gets about 89% accuracy. Whereas if you use distributed SGD type of algorithms, you get about 87 or 87.5 accuracy, suggesting that, you know, federated average is a better for personalization. And in this follow-up work by my collaborators, this can be made precise in a similar way how MAML was learning a representation can show that if you do more than or equal to 2 local updates, then federated average recovers the ground truth representation under this linear representation learning setting. And the intuitions are similar. So for these two algorithms that were designed in two completely different contexts, MAML for meta-learning, federated averaging for federated learning, for two completely different motivations, both seem to work well in practice and widely used. And by putting this lens of linear representation learning and theoretical lens to these two algorithms, we were able to show that they, the first one, MAML, learns good representation, and the results showing that federated averaging also learns good representations. So this is maybe one perspective of why these popular algorithms work well in practice. And perhaps this will shine new light into understanding these algorithms. And with that, I think I'm ready to take questions if there are any.
Thank you very much, Sewoong. Are there any questions from the audience? Please type the questions in the chat box, in the Q&A section.
Very nice talk, Sewoong. I have a question. So I guess in both of these works, you assume that there is some common representation. I guess you call it B, and then each one gets multiplied by another W or something like that, which you call the head. Is there a that's a nice way to think about it. So basically, that's a common thing that everybody learns, and then you fine tune to learn the W's. But I guess, is there a direct way of thinking about it in terms of generalization error? If you can sort of say that there is, each of them has a data set that is has some distribution, but the distributions have some distance between them. I mean, they are not very far apart, which is sort of what this B is capturing in some sense, right? B is capturing something common, and then W is capturing something slightly different. But I guess in practice, it may not be like that. I was just wondering if is there another way to model this? I guess where you could say that the distributions are all slightly different from each other, but there is something common about them, and then doing this process where you do more iterations locally, and then doing outer loop. I don't know, whichever you call that. Yeah, where you do something every now and then that actually can lead to better generalization than all together.
Mm-hmm. So theoretically, I think this is one of the very first result in any analysis of these algorithms with adaptivity. I believe there will be much more coming following. So this is the only case, this linear representation is the only case we could show anything, or anyone could show anything. I believe the same should go through for nonlinear representation. If you assume there's a nonlinear representation that's shared across, I believe the same analysis could show some generalization, and that is plausible. Beyond that, even in a simpler settings, I haven't seen anything theoretically analyzable that proposes a model that generalization error is tractable. Although the formulation, if you look at the original kind of formulation of MAML, there's two perspectives. One is this gradient perspective, which kind of is intuitive. The other is actually the intuition that you're saying, which is that they assume there's a distribution of data, and every task is coming from that distribution. And anything else is captured by that joint distribution of X's and Y's, whatever it is, it's in there. And then they try to reason about these algorithms and how we are learning posterior probability, and they put some probabilities in there. So there is empirical and heuristic kind of directions that tries to do that. But I don't know if there's any theoretical lens that can be put in, because it's really hard to define a joint distribution that's non-trivial and that can be analyzed through the lens of generalization.
Okay.
Because you need to tell them how is task 1 and task 2 related yet different, and that is hard. So kind of VC dimension type learning theory perspective of meta learning, I do not know of. Although you can do it if it's a linear representation, you can bring those lens and do it. So you can think of ours as one specific example where such thing is doable.
Okay.
But in general, I haven't seen any generalization bounds that can tell you anything.
Okay, thanks.
There's one question in the chat from Virgil Chen, who's asking, might the joint distribution help solve the problem that MAML is computationally heavy in the gradients? I'm not sure I understand the question. Maybe I will allow the
joint distribution helps solving the problem that MAML is computationally heavy.
Yeah, Virgil, you're permitted to talk in case you want to clarify your question or have a follow-up.
You're muted if in case you're talking virtual. Yeah, maybe he doesn't have access to.
Okay.
But
Oh, mic is not working. Okay.
oh, so yeah, I cannot pinpoint exactly what the question is addressing about computational heaviness.
Maybe this is related to the Hessian computation.
Right, so we can drop the Hessian so that it's not computationally heavy, and that's the first order MAML that we show works well in this setting also. That's the short answer. But I think he meant something deeper about joint distribution, which I couldn't pinpoint.
I also have a question. Okay, maybe, but he's trying to clarify. Maybe I'll ask my question while he types in his clarification. So in the first part of your talk, you showed that ANIL, because it considers this explicit representation that is shared, does better than MAML for representation learning. And then in the second part, you said that Fed averaging is doing something analogous to MAML. So do you have any thoughts on an analog of ANIL in the federated setting that would also potentially do better by learning shared representations?
Right. So there is a complete representation-based algorithm like alternating minimization. And ANIL is somewhere in between. And then MAML is up here. And so MAML and this representation algorithm, there are counterparts to federated learning. MAML is federated averaging. Complete representation learning would be what's called federated reconstruction. ANIL, I'm not aware if particular ANIL that's somewhere sitting in between has been tried out and there was any gain. I think it's worth trying, especially for personalization, but I haven't seen that.
Okay, thank you.
Right.
I think we have no other questions. Oh, Virgil is clarifying.
Are there any?
I think he means the Hessian higher order, probably.
Right now, on the top of my head, I cannot make the connection between the distribution-based, it's called probabilistic approach to MAML versus MAML, how the updates are exactly related. So I cannot comment on the computational complexity of these two. But usually it's not for computational efficiency that those algorithms are studied. It's usually, if anything, more complex because you're looking at the distribution, but hoping that you capture something that's missed by MAML. And I think that's all the answer I can give at this point without remembering exactly how those methods work.
So let us thank the speaker again. Thank you very much, Sewoong, for a very
Thank you.
interesting and insightful
It's so great to
talk.
see you both. So I'm just so happy.